Hi guys, we are going to do a little bit of, I guess you'd call them notes on chapter 20. You have already read hopefully the first section, and I know you're familiar with a lot of these words already, but we are going to be talking about today solutions. So first of all, a solution is a type of mixture. It is homogeneous, which means that to your eye, if you are looking at it, it all appears the same. Even though you have two different substances in there, one of them at least dissolves so well or mixes so well that visibly you only see one face. For example, Kool-Aid. When you make Kool-Aid, you are putting a solid into a liquid. But when you look at it, you don't see the solid pieces. You don't see the liquid. You just see one thing, and it's just Kool-Aid. So that's a solution. And in a solution, you have two parts: the solute, which is the substance that is being dissolved. And so in our Kool-Aid example, that is the actual powder. Sorry, I'm trying to write this with my finger. It's not the greatest. And then the solvent, the substance that is doing the dissolving, is, in our case with Kool-Aid, water. So in general, sometimes they will say that the solute is present in a smaller amount, and then the solvent is the larger amount. It's just kind of one of the ways they differentiate between the two. In your reading yesterday, you talked about like the dispersed phase, or you read about the dispersed phase and those kinds of things. Same thing. You know how science is, it just likes to have a bunch of words for the same thing. So try and kind of keep them straight in your mind. Now, with solutions, chemically, there are things that are called true solutions. We call lots of things solutions that wouldn't fit all of these characteristics, but a lot of them will. The example I want you to think about for this one is salt water. And so with these true solutions, salt water is the best example. First of all, you have a solute that will not dissolve, or excuse me, that you cannot filter out from the solvent. So if you ran it through filter paper, it would come out salt water on the other side. You wouldn't get anything stuck in that filter. Second, if you took this salt water and you put it under a microscope, even a really good microscope, you would not be able to tell the difference between the solute and the solvent. Also, the solute does not settle, which means that the salt will not settle down at the bottom. It is something that is clear or transparent to light. You don't necessarily have to see right through it, but you should be able to see light through it. And this is true, this next one is true for any mixture. It has a variable composition. That variable composition means that in every cup of salt water that I have, I will not always have the exact same amount of salt versus water. It will always vary. I can separate these true solutions by evaporation. If I let the solvent evaporate away, then I will be left with the solute. And then the last one, the true solutions can be identified by the particle size of the solute. There's probably a chart in your book, I forgot to look it up. But basically, the particle size of the solute in a true solution would be something ridiculously small, you know, like 1 nanometer or 1 pico or picometer, or you know, something like that, super, super small. Like I said, lots of things that we call solutions aren't necessarily. One of the other types of solutions, not a true solution, is a suspension, and this is where you have large solute particles. Again, there's a measurement, and if those particles are so large that eventually they settle out. So if you think about things like orange juice with pulp in it, that's a suspension. If you have to shake it up to get everything mixed, that's a suspension. So like salad dressings, medicines that you have to take a liquid form of. But so these were the true solutions. All right, so now the types of homogeneous mixtures, so the types of solutions. They can be a solid, a liquid, or a gas in their phases, and that the type of solution would be determined by what the solvent is. So if it is a solid solution, the solvent is a solid. All right, so now, if we're talking about solid solutions, in general, and I'm sure there are exceptions, but in general, the solvent is usually a metal. And so some examples, hydrogen, of course, is a gas, and you can dissolve hydrogen in, well, come on, you can dissolve hydrogen in different metals, platinum, palladium. They are used not to really make a new substance, but to purify the hydrogen as it passes through those metals. So that is considered a solution. Mercury is, excuse me, a liquid. Remember, it's one of the few liquid metals. And it dissolves into silver and to gold. These, excuse me, liquid and solid solutions excuse me, are called amalgams. If you've ever had a filling in your teeth, if you had a cavity, a lot of times they call them amalgams. They don't use mercury anymore. They used to have mercury fillings, but then they, found out all the bad stuff about mercury. But so mercury can dissolve into other solids. And then you have metals that can be dissolved into other metals. And you guys are pretty familiar with all of these. If you have a solid and solid solution, two metals mixed together, those are called alloys. That is usually done because you want to strengthen those two metals. Together, they will be stronger than the individual metals themselves. Okay, so now the next type of solution is a liquid solution. It is by far the most common. For the majority of us, I think when you think of a solution, you're going to think of a liquid. In these liquid solutions, the solvent is usually water. Again, this is because water is so common, and we'll talk about it in a minute, but water is really good at dissolving stuff. So with liquid solutions, you can have all three states of matter as the solute. So if you were dissolving a solid into a liquid, you would have something like salt water. And that solute, in this case, solid is sodium chloride, so that's just salt. And so when you put it in there, it will dissolve. You cannot see the salt anymore. You aren't aware that it is there. It will just look like water, but it's a solution. You can also have a liquid in liquid solution. And so if you're dissolving another liquid into water, for example, you probably would want to think about something like vinegar. Vinegar is very common, and you probably have some in your house somewhere right now. If you went and looked at it, it would somewhere on the label say something about acetic acid. Acetic acid is a liquid that is dissolved in water to make vinegar. By itself, acetic acid is just too strong to use, but so when you dilute it with water, you make a solution that is useful. And then you can also have a gas as the solute. So if you drink carbonated stuff, Cokes or Sprites, whatever it is, along with all the other ingredients in there, the bubbles come from the gas solute, which is just carbon dioxide. And so liquids, again, very common to think of those as your solutions, and they're probably the most diverse group as far as we're concerned. Now, gas solutions. These are pretty limited because in a gas solution, the solute and the solvent have to both be gases. You cannot mix a liquid or a solid into a gas as the solvent and have it stay. I could not say right now, okay, I want to make a solution with a solute of salt and a solvent of air. That would involve me basically just throwing some salt into the air to see what happens. The salt will hit the ground because it cannot dissolve into the air because of gravity. So you're kind of limited. It has to be a gas and a gas. For these gas solutions, air is the most common example. Air is made up of lots of different gases: nitrogen, oxygen, CO2 that you're breathing out, water, some other little trace amounts, but they all have to be gases for the solution to stay together. All right, now water. Water is a big deal in solutions because it is the universal solvent. And we call it the universal solvent because it can dissolve more substances than any other solvent that we know of. Also, water is just extremely abundant. It is pretty much available all around the world, and so we know that it can dissolve a lot of things. water is never truly pure. So even if you purify your water, even if you go to the store and you buy some kind of distilled water or purified water, it's not ever truly pure because it is constantly, whenever it is in contact with another substance, dissolving it just a little bit. Even, stainless steel, the specialized plastics that they use now in water bottles, they are still dissolving, not as much as other substances, but there is still a small degree of dissolving happening. So that water is never pure. You are mostly water. I think we've talked about this before. The human body is about 60% water. Of course, with varying degrees in there, your bones are only around 30% water, whereas your blood, of course, is a much higher percentage water. And so average, though, 60% of you is water, so hopefully you like it. Okay, so now, water is very good at dissolving stuff for several reasons. Those reasons all have to do with its molecular shape. So down in the corner there is a water molecule drawn. That's the molecular shape. That should look a little bit familiar. The orange dots on there are the electrons of the oxygen, and then the little pluses are the electrons of the two hydrogens, so they're all together. Of course, that water is two H's and one O. And when they form, water molecules have kind of a bent shape, or kind of like an angular shape. Oxygen is in the middle, and then the two hydrogens attached to it. Now, oxygen is more electronegative than the hydrogens. And remember, on our periodic table, we marked this. The upper right-hand corner is where the more electronegative elements are, and oxygen is right up there. And so it has a stronger pull on the electrons, and it keeps the electrons, even the ones that they're sharing, keeps its electrons closer than the hydrogens do. And so because the electrons are all closer to the oxygen has a negative charge, a little negative on there, and the hydrogens both have a positive charge. So they've got a positive side. Now, if you were to draw a line like right down the middle there, you would have two halves, or two sides of this water molecule. And so very often you will hear people say that water has a positive pole, or a positive half, that's where the hydrogens are, and a negative pole where the oxygens are. And so it is technically classified as a dipole, so two poles, polar molecule, because it has those two charges. Now, the whole process of dissolving things is it's kind of complicated, really, but super quick. So it happens very fast. When you are mixing water with sodium chloride, the water itself, the H2O, breaks the sodium chloride apart because the oxygen, and they are the little red dots over there in the picture, attract the sodium, and they are the purple dots. So you've got a negative and a positive. And then the hydrogens are kind of the little whitish, kind of grayish dots. They are attracted to the sodium, which are the big green dots. And so they are basically switching places. They are being attracted to the other substance because of charge. This whole process is called dissociation. And I forgot to highlight that one, but they are called this is called dissociation. And that's the process by which the ions in an ionic substance like salt are separated from one another. Now, this little video link, I'm not going to click on it because I'm not quite sure how that'll work, but hopefully if you can't click on it, if you'll paste it into YouTube or search it up on YouTube, it shows a really simple video of this whole dissociation process. You'll probably laugh at the graphics, but it's a pretty good explanation. All right, now last thing, solubility. Not everything forms a solution, and part of this is based on the solubility. So to be soluble, a substance has to be able to be dissolved by a solvent. So I have to put them together and have the two things dissolve. And solubility is a measurable thing. It is the maximum amount of solute that will dissolve in a given amount. and it usually will have something to do with temperature. And you guys probably know that if you heat up water, you could dissolve more sugar in it than if it was cold water. So temperature is kind of a big deal. There are some limits to solubility. Some substances are soluble in each other no matter what. So if you put them together, they will form a solution. This is called miscibility. Substances that are miscible because they have similar structures. They are both polar, or they are both non-polar, they are both ionic, whatever it is. And a lot of times you'll hear people say like dissolves like. So if they are alike, they will dissolve each other. Alcohol and water are a good example of this. They're both ionic compounds or both polar compounds, and they dissolve very well. But there are substances, like we said, that do not dissolve. This is called immiscibility. And with this, you have things that are not alike. And so one may be polar, one is non-polar. The easiest example of this is oil and water. If you put oil into water, one will sit on top of the other. You can shake it and make the oil mix down into the water, but if you let it set for any length of time, the oil will rise to the top again. They are immiscible. All right, so that is the first part for chapter 20. Let me know if you have questions.